We can analyze the behavior of LTID systems by their frequency response. In the time domain, the output y of k is equal to the convolution of the impulse response h of k with the input signal x of k. So in the frequency domain, y of omega is equal to h of omega, which is the frequency response of the system, and the discrete time Fourier transform of the impulse response h of k times x of omega. So the frequency response h of omega is defined to be y of omega divided by x of omega. Let's consider this example where y of k plus 2 minus 3/4 times y of k plus 1 plus 1/8 y of k is equal to 2x of k plus 2. Applying the discrete time Fourier transform yields that e to the power of j 2 omega minus 3/4 of e to the power of j omega plus 1/8 times y of omega is equal to 2 times e to the power of j 2 omega x of omega. The frequency response h of omega is given by 2 times e to the power of j 2 omega divided by e to the power of j 2 omega minus 3/4 of e to the power of j omega plus 1/8. And again, h of omega is a complex valued function of omega, for which we can draw the magnitude as a function of omega and the phase as a function of omega. Note that h of omega is now a periodic function in the frequency domain with period 2 omega. Despite that, many principles to analyze the behavior of this system through the frequency response still holds the same way as for LTIC systems. This system, for instance, passes low-frequency components and attenuates higher-frequency components. So this system could be interpreted as a pretty bad low-pass filter. In order to judge which kind of filter a DT system represents, only the frequency range between 0 and pi is of interest. Because h of omega is periodic and symmetric, the frequency range between pi and 2 pi is just going to be the frequency range between 0 and pi mirrored, and the frequency response for all other frequency ranges is merely going to be a periodic repetition.